Today, we're really excited to have Professor Broxton Bird with us. My name is Steve Vieweg. I'm the Associate Director of the Center. It's my pleasure to welcome you all here as we dive into our session today. I'd like to give you a little bit of background information about who we are and where we came from. The Center for Translating Research into Practice is the brainchild of Professor Emeritus Sandra Petronio, herself a translational scholar. And she was the founder of the center when she came to campus along with her husband, former Chancellor Bance. She observed that our campus was probably one of the most translational campuses they had ever visited in the past and ever been a part of. And that's likely because we have a lot of work that is in partnership with our community and that makes a difference for folks. We generate and take evidence to help solve problems. Former Chancellor Charles Bance is the executive director of our center right now, and he is continuing to take the lead in encouraging that this sort of work continues on at IUPUI, and that we all can continue the legacy of bringing out research that is translational, that makes a difference for folks in our community. As we get started today, just a couple reminders about Zoom etiquette. We all know, but please keep your microphones muted. Although at some point during conversations, when you're invited to share, we hope that you'll unmute and turn on your camera so that we can see you and you'll participate in the conversation. You're of course welcome to put your questions or observations in the chat. And at the very end, we'll hang around a little bit once we end for those that want to stay as well. We are recording this presentation today for those who would like to see it again, or maybe you know folks that weren't able to come and would like to attend at a later date. Of course, you'll be getting one of those post-evaluation event forms in the email, and we hope that you'll take a moment to fill that out to give us some feedback about this experience and some support for what we should do next. You can get continuing education credits for this whole series. All you have to do is visit expandiu.edu and look for the trip-CEU. And there's always lots of things going on at the center, and we hope that you'll follow us in whatever way is best for you. On social media, you can follow us on Facebook, Twitter, Instagram, and all of our sessions that we are able to record are on our YouTube channels. You can always check it out later. We had just recently participated in IU Day. What a wonderful opportunity that was to support the many programs at IU. Our efforts were able to raise $5,470 toward the Bance Community Fellowship, and it's not too late. People could donate if they wanted to. It's amazing work that goes on. You should check out our website at trip.iupui.edu so that you too could know more of what's going on at our campus and some of the amazing work that is in partnership with the community. One of our features in our center is the Scholar Works opportunity. So if you go to the featured page and you were to click on Broxton Bird, our featured person today, you will see on that page a whole list of his journal articles that are available to you by clicking on a link. You don't have to go to the journal or to the library. You can just go straight to this website and see it. You can also click at the top there to the page for ScholarWorks and see some additional works that he has put there. And that's true with all of our scholars. This makes it very easy for you to keep up to date on their amazing work that they put into journals at the click of your hand. Next month, we have our regular Scholar of the Month on May 26th at noon. We're featuring Professor Silk Soto, and she's going to be leading a conversation that's titled, I Am Interested in Helping Restore Trust, Perspectives on Trust and Trustworthiness in Biomedical Research. So put that on your calendar. We hope that you'll join us for then. But today we are super excited to have with us Professor Broxton Bird, who is an associate professor of earth sciences in the School of Science. And he's going to lead us through a conversation that I know will be very interesting to you. So welcome, Broxton. We're so glad that you're here.
Hello, hello. Great to see everybody here. Thank you so much. I will share my screen here now. And as we said, this is a conversation, right? So as there are questions or as I go through this talk, this really is not just me talking at you, but it really hopefully will spur some conversation. And, so definitely unmute and ask questions as they arise or type them in the chat. That will be monitored, fortunately not by me, because I know that's difficult to do while you're talking and all that. So unfortunately, we have the great Trip team here to help us out. So yeah, it's really a pleasure for me to be here today. I'm excited to talk about some of the research that I am doing, but also really this is a group effort that this is being undertaken as. So I feel like I am more of a representative of a larger group of folks that are working on these issues that I'll be talking about today. This is my title slide here, and one of the reasons that I've chosen this image is that, you know, we often see maps perhaps of the United States, things like that, but we don't often think about the watersheds in which we all live, right? Every single one of us on Earth lives in some watershed or another. Some of the main ones here I've highlighted are the Ohio River, the Missouri, the Arkansas, all of which drain into the Missouri River. And then the lighter colored white lines in this image also show sort of the smaller ones, right? So we'll be thinking a lot about different watersheds of scale and the climate processes that influence these range of different watersheds and how they influence us who live in these watersheds here. So to start though, right, one of the things that I think is important to talk about first is really what is paleoclimatology, right? So again, you know, you can unmute, you can type in the chat, but you know, what is paleoclimatology as a science, right? If anybody wants to shout out, they can. If I don't hear anything, I will continue on. But really, paleoclimatology is a branch, really started as a branch of geology, right, that is interested in investigating past climates, right? And not just what they were, but also how they have changed over time. So as a science, paleoclimatology was really born in the 1800s. And a lot of this was driven first in Europe. And some of the impetus for this was the recognition that there were these landscape features. I'm going to change my pointer to a laser here. So some landscape features that appeared to have been formed by glaciers in the European Alps, even though there were no glaciers currently present there. And so this led to the idea that there had once been periods of glaciation where glaciers had expanded out of the Alps and down to lower elevations and subsequently had retreated. And subsequent work has found that this happened about 20 or so thousand years ago during a time period that we refer to as the last glacial maximum. We use lots of acronyms in science generally, but definitely paleoclimates. So the LGM, last glacial maximum, right? And as these glaciers retreated, they left behind landscape features that intrigued geologists in the 1800s to try to explain how these things were happening and why they were happening. So relevant to this, again, today, our climate is changing again, and ice is, again, one of the canaries in the coal mine, one of the main indicators, or at least some of the most visible indicators of this change. So this here is an image of the Alpha Glacier in the Chilean Andes from about 1953, and I've included the CE there just to refer to the Common Era, which is the last 2,000 years. And then we can see today, or relatively today, from 2019, we have a reduction of over 60, almost 70% in the aerial extent of this glacier, right? So these are really canaries in the coal mine that show these massive changes that are happening today, right? But we also have our shared experience, right? The climate that we are experiencing today, especially for some of the more experienced generations, I'll phrase it that way, is different than the one that we grew up in, right? So this is a temperature graph of from NASA showing global temperatures since about the late 1800s. And what we see is this general increase, right, from the early 1800s into the 1900s, and then steeply increasing after about the 1960s or 70s today. So if we think about this from a generational standpoint, right, the silent generation, the baby boomers, Gen X, right, these three generations all were born within a generally similar type of climate regime. Subsequent generations like the millennials, Gen Z, and our current alpha generation, right, have all been born under different climatic regimes, and they really trend with this increase in temperature, right? So we are experiencing the climate today that is fundamentally different from the one that many of us grew up in. This is on less of a global and more of a local here in the Midwest sort of perspective, right, this is really also being felt in terms of certain changes like precipitation, right? So precipitation in the Midwest since the basically varied about a mean from about the 1900s, and around the 1970s or so started increasing decade upon decade, right? This is also observed in things like heavy precipitation events, right? So varying about a mean up until about the 1960s or 70s, and then decade upon decade increase to today with increases in extreme precipitation, right? So we can tell that the climate that we are growing up in today or existing in today is different than the one that many of us may have initially started growing up in. So one of the questions, right, that we might want to ask is, what can we actually get from paleoclimatology, right? Why do we want to study past climates, right? What can we learn from this study, right? We see that our climate is changing today, but what use is there really in studying some of our past climates? So if anybody has any thoughts about some of the utilities of this, you can throw those out there. What are some of the things that we can learn from paleoclimatology? What might somebody want to know, right? Maybe something, I'll throw out a theater question there. Maybe we want to know how different, right, past climates were. We know that our climate today is changing, right? But how different was climate in the past? We saw that there was evidence for extensive glaciers, right? So that indicates there must have been some pretty massive changes, right? So another question might be, what is the range of different climate states, right, that we have experienced here on Earth, right? What is the natural range of variability that we could experience? And how does our current climate compare with those that existed in the past? And this could be the recent geologic past, which for geologists is the last few thousand years, or the distant geologic past, which could be several millennia to millions of years, or even billions of years in the past, right? Some of the other things that we may be very concerned about, even though we may not think about it often, are the rates of change, right? As I often say, it's not the fall that killed you, it's the sudden change and acceleration, right? It is the stop. So it's not about the absolute change, it's about the rate of change in which you stop. And so as we go through our current climate change, right, we have gone through changes in the past, but how quickly we go through those changes can have tremendous impacts on the landscape, on the biology, on the flora, the fauna, all of those things, right? So we may want to understand how quickly our climate is changing. And fundamental to all of this, right, is what are the causes, right? What causes climate to change? What is it responding to, and what is driving these changes? And naturally, right, probably one of the things that most of us are concerned about, especially those that have children, families, whatnot, right? What can we expect for the future, right? How can we adapt to the climate changes that are going to occur, right? First, we need to understand how or what climate changes are going to happen, what is predicted, and then how can we adapt to these, right? To sort of address these questions, right, what we really need is data, right? And we have some data, right? I've already showed our temperature graph going back to the 1800s. So we have some data, right? But the instrumental records that we have typically only span about the last 100 to 150 years. This is much too short. In paleoclimate jargon, this is what we refer to, this time period, the last 100 or so, 200 years, is the current warm period. So in order to investigate climatic states before that and the relationships that cause climate to change and the responses, right, we have to have climate data that extends beyond the paleoclimate record, right? But how do we do that? How do we extend, in this case, maybe temperature records back in time to see what variability would have been like in the past to understand where we are? But before we sort of talk about that, right, what do we want to know about, right? Temperature is one thing, right? But what defines our climate today? So I'll ask you, sort of the general audience here, what is climate and what defines our climate? How do we think about climate? What does that mean to you? I'm also trying to look here in the chat to see if there are any answers. So what is climate? When we think about climate, you think about an area of Florida versus... Okay, yep, temperature is a great one, right? We definitely think about temperature. We have the NASA temperature. There's sort of two main ones, right? And temperature is one of them. What's the other one? What's another?
Precipitation?
Yeah, maybe moisture, right? So these are sort of the two main ones. And when we talk about climate, right, a lot of us don't think about what the definition of climate is, right? Temperature and precip are very important, right? But when we talk about climate, what we're talking about is not weather, right? We are thinking about the average of weather over a long period of time. And the standard definition that is used for meteorological climate today is about the last 30 years. So we take about a 30-year average of weather. Now, when we're talking on geologic timescales, climate could be over 1,000 years or longer, things like that. But temperature and precipitation are two of the main ones. But some of the things that we're really interested in beyond just these is not just temperature and precip, but really we're thinking about the amount of precipitation that occurs, when that precipitation is happening, so the seasonality, and the phase. And by that, I mean, is it rainfall or snowfall, right? What type of precipitation is falling, right? All of this influences many things, right? For example, the vegetation on the landscape, right? We think about the desert Southwest, right? That has low precip, high temperature, and, arid vegetation, right? Here in the Midwest, we have our eastern temperate forest, right? Because we have warm temperatures, but highly seasonal with ample warm season precipitation. So all of these act together to influence our landscape and our vegetation, right? But we are also concerned about extremes, things like droughts, too little precipitation, maybe too high of temperatures, right? Or the opposite, floods, too much rainfall, right? Things like that. So we care about some of these extremes as well. And super important with this from a paleoclimate perspective is trying to understand what kind of atmospheric circulation conditions lead to the average types of climate that we have, average temperature precip, but also the types of extremes that these climates can experience, right? What types of atmospheric circulation cause floods, cause droughts, other types of things like that. So some of the things that we need to know about, right, are also things like how the oceans are responding during these times, right? Ocean circulation, temperatures, right? All of these interact with the atmosphere to produce our average climates in different parts of the world. And when these act together, there's a concept of teleconnections within our climate system that is really critical for understanding climate variability through time and climate change actually as it's happening today. So teleconnections is a fancy word for describing interactions between the ocean and the atmosphere that can have impacts far from the location where these actual variations are happening. So that sounds very complicated, but you've all heard of El Nino, La Nina, right? So this is sort of the most iconic or classic teleconnection, right? So we have changes in the Pacific Ocean atmosphere system in the tropical Pacific, right? But these don't stay there. They have tremendous impacts. Here I'm just showing North America, but they have tremendous impacts on the distribution of temperature, precipitation, and a lot of this has to do with the orientation of the jet stream, right? So through these temperature variations in the Pacific, we can influence our weather patterns and climate patterns through time. And importantly, there are various types of ocean atmosphere variability in the Pacific that look like El Ninos and La Ninas, but can last for long periods of time. And we'll come back to that because that will be very important for us. Right, so those are some of the things that we want to know about. We want to know about temperature, precip, ocean, atmosphere processes, things like that, right? But how do paleoclimatologists reconstruct these different types of variables through time, right? We can't just go out there, right? We can't measure temperature. We can't measure precipitation directly. If we had time machines, it would be awesome. It would answer a lot of questions very easily, but we can't. So we have to sort of create what we call proxies, or we have to use proxies that are essentially estimates of past types of climate conditions, right? So when you think about proxies, these are different types of biological materials, chemical materials, physical materials, right? That can be correlated to a specific climate variable or an environmental process, right? So they're not actual rainfall, but it's something that might be sensitive to rainfall. And so it can tell us about rainfall variability through time, for example. So these are our data, right? It is essentially our weather station data that we can produce indirectly that will span time, right? So if we're thinking about biological process or proxies, right? Can anybody think of any biological systems that might respond to climate or that paleoclimatologists might use for reconstructing climate? Any examples of what a biological proxy? I'll give you one to maybe spur you on a little bit. Pollen, right? So like plants produce pollen and the types of plants that are on the landscape will be sensitive to the average temperature and precipitation of a region, right? The pollen in the desert Southwest is going to be very different from the pollen here in the Midwest, right? What's something else maybe you can just shout out to?
We've got vegetation types, tree growth rates, migration and breeding seasons, and tree rings in the chat.
Yeah, I love that. So the growth rates, that was a great one. That was my next pop-up here, right? Was tree ring width, right? How quickly trees grow can be dependent on the temperature or the moisture availability to those trees, right? You may not have heard as much about these, but little single cellular creatures that live in lakes, soils, all sorts of things called diatoms are really sensitive to light conditions, moisture conditions, wind, cloudiness, all sorts of different variables, right? So these are some really nice ones that we can use. So this is just a selection here. When we're thinking about chemical proxies, right, we have lots of different isotope systems, both stable and radioactive, right? So we're thinking about chemical processes, reactions that may be temperature sensitive or sensitive to the amount of moisture. There are lots of organic geochemical proxies, lipid biomarkers, all sorts of things, right? All sorts of different organisms are living in different environments, and their remains are preserved through time. So we can measure those with organic chemistry, right? Inorganic chemistry, mineralogy, right? Many different things within these chemical processes that can respond to temperature and precipitation. And we also have physical processes or proxies, right? So things like changes in stratigraphy, what sediments actually look like, right? If we go from laminated sediments to massive sediments in a sediment core in a lake, right? This might reflect changes in the environment of the lake that then are being driven by climate, right? The energy of the environment, right? Think of a beach versus the middle of a lake, right? These are going to be two very different energy environments, sand on the beach, clay in the middle. So we can think about things like lake level changes. One thing we'll be talking about today are accumulation rates, right? How quickly sediments are accumulating, especially in river systems where flooding is occurring, right? We can relate these accumulation rates back to the frequency of floods, right? And of course, as we began with, thinking about landscape features, things like glacial moraines, glacial features, things like that indicate very different climates in the past. But the important thing is that all of these different types of proxies, and again, this is just a few in the toolbox that paleoclimatologists use, these are different materials, processes that are related back to a climatic process, right? So we cannot directly measure temperature, but these are things that may be sensitive to things like temperature. So we can construct our data, right? But we have to preserve those through time. And so one of the ways that these are preserved is through natural archives, right? So we have our instrumental data today that we can preserve digitally, right? But as we go back in time, we have to rely on these natural archives. So some natural archives, I'll just kick one off that many people have probably heard of, right? Glaciers, ice caps, and the ice cores that come from those, right? What might be another natural archive that paleoclimatologists could go to in order to try to reconstruct climate? What might be another?
Well, somebody had mentioned in the chat the ice layers and the stomatal density of plant leaves.
Yeah, excellent. Those are really good, right? So stomatal density, where the CO2 is exchanged with the atmosphere, right? Higher CO2 or less CO2 will change the density of those. Absolutely. Yeah, fossils are a great one. I'm seeing that there. Excellent, right? Another one is tree rings or trees, right? So at the growth rates, as trees grow faster or slower, they preserve their tree rings and the width in time, right? Corals, for example, maybe a little less familiar here in Indiana, being so far from the ocean, but these are very important for ocean conditions through time. And then, of course, there's lots of different types of sedimentary basins, right? So basins on land, in the ocean, that accumulate sediments over time, right? And so we can think about things like ocean sediments, lake sediments, of course, bog sediments, any different types of sediments that are actively accumulating. But then, of course, for deeper time types of paleoclimate work, we have our ancient sediments that are exposed as outcrops that we can go back to, and in some cases to look at some early climates from even the beginning of the Earth from 3.84 billion years ago. we can look at very deep time types of climates with these ancient sediments. And then some novel types of proxies or archives are things like pack rat mittens, especially in the desert Southwest. These little small rodents collect the materials that grow within a limited range of their homes, and they bring that back. And so that can actually be used to reconstruct local climates through time. And the important thing is that all of these archives reconstruct or at least preserve these different types of climate proxies through time, right? So when we're thinking about sediments, we have this law of superposition that we talk about in geology, where it simply means that the older sediments are at the bottom and that younger sediments are accumulated on top of older sediments. So the top of a sequence is the youngest and the bottom is the oldest. And this works with other things like tree rings, right? Where the inner part of the tree is the oldest part that first started to grow, and you get younger as you work your way out. Same thing with corals. As they grow, they build outwards, much like a tree ring as well, on an annual scale usually. And so we can actually use these to go back through time to measure proxies through time to get at a variety of different types of information. And where these different types of archives are located really determines the type of information that they preserve. So as geologists studying climate, when we want to know about specific climate processes in different and specific parts of the planet, we will go and target different types of archives in order to generate these data. So my research specifically, right, as a paleoclimatologist is focused on lake sediment archives, right? So I use lake sediments to reconstruct past environmental and climatic conditions. And one of the things that is great about lake sediments, right, is that they integrate signals from their watershed. And we'll talk about watershed scale in a second, but the point is that whatever climatic processes are happening, right, in that over that watershed, whatever types of changes in vegetation or type of vegetation is there, if there are changes in flooding, which we'll talk more about, changes in land use, basically anything that is happening within that watershed, if it is of a sufficient magnitude, will be recorded and reflected in the lake. And so these are really valuable. These types of archives are really valuable for understanding sort of these large scale watershed scale types of processes. So when we think about watersheds, as I showed in my first slide, right, there are lots of different scales of watersheds, right? You can have watersheds that are micro watersheds to huge watersheds, right? So here in Indiana in the Midwest, right, two great examples of these and which are watersheds that we've been working are the Ohio River, right? So the Ohio River is a huge watershed, about 500,000 square kilometers. It is massive, truly one of the largest watersheds in the US, third largest. We have also in Indiana, the White River, right? Nestled within the Ohio River watershed, different scale, 30,000 kilometers. And then we have other smaller types of watersheds like Martin Lake, which has only a 12.9 square kilometer type of watershed. So the processes that are going to affect watersheds depends in part on the scale, but only in part, because sometimes even small lakes, as we'll see, like with Martin Lake in a minute here, sometimes even those with very small watersheds can preserve information about very large scale processes as well. But when we put them all together, we can really think about different types of scales of processes that are impacting the landscape and people. So when we use lakes, as I said, right, there are a range of different types of lakes and different types of scales, and we target different types of lakes to answer different types of questions, right? So some of the work that we're doing on lake glacial and Holocene climate over the last 10 to 20,000 years is focused primarily on what we call kettle lakes. So kettle lakes are lakes that are formed in regions that were once glaciated by large continental scale ice sheets, like the Laurentide ice sheet that covered much of Indianapolis in Indiana about 20 or so thousand years ago. And the idea behind these is that as those glaciers retreat, they leave behind blocks of ice that are buried in the landscape. And as they melt, they leave behind depressions that eventually turn into lakes. And so these lakes date to about 16 to 20,000 years or so in this region of the United States. Which is when the glaciers left this area back then. So a classic example of these, and one again, which we'll be talking about, Martin Lake here, which is part of the Oliver chain of lakes in northeastern Indiana. In other parts of the world, like the Himalaya and the Andes, where I also do work, we work primarily with cirque lakes, which are simply gouged out by glacial activity during glaciers, and when they retreat, again, they also leave a depression in the landscape that accumulates sediment through time continuously, and so we can go back, core those, and then reconstruct climates through time. For flooding reconstructions, right, we go to floodplain lakes, and we'll be talking more about these. These types of lakes or river systems in general are typically very active, and we'll talk more about stream mobility in a bit. But some of the iconic types of lakes are oxbow lakes. So this one here, which we'll talk about, Half Moon Pond here on the White River in Indiana, is formed very much by this type of process, where we have initially a very meandering river that eventually over time cuts off the meander to form a new river channel, leaving behind an old lake on the watershed or on the floodplain, that when that river floods, it collects sediment from those floods. And so the rate of sediment accumulation in these lakes is directly linked to the frequency of flooding. So these are really valuable records for paleo floods. We also have another one, Avery Lake, which we'll talk more about. This is a meander scar lake. So in this area up here where I'm pointing to, right, as these rivers sort of build out over time, they leave behind these linear lakes on the landscape as well, also subject to flooding. So lots of different processes, but still recording flood information. We won't talk about this lake today or these timescales, but if we do go deeper back in time, like hundreds of thousands to millions of years, we have to rely on tectonic lakes. So these are formed by movements of Earth's crust, either expansion or deformation of some sort. So we are working on Lake Tota in Colombia, which is probably about 1 million to 1.5 million year old lake with almost 300 or 400 meters of sediment in it. So these are very long-lived lakes that we can address questions spanning several hundred thousand to millions of years in some cases. But for this lake, this talk, we're gonna focus mostly on some of the work that we're doing here in the Midwest on some of our floodplain and kettle lakes. But we do this work, as I said, all over the world, right? So we're working in North America, South America, Asia, right? To understand hydroclimate change through time, fluvial changes through time, and the human influences and responses. So one question for you all is, what connects these seemingly very disparate locations, right? And I'll give you a hint, they are connected, right? So we have 3 different continents, right? Tropics to mid-latitudes. But what might connect these locations, these study locations? I put them a little bit out of order, but.
You said mountain ranges?
Yeah, so mountain ranges can be one, right? So we do have large mountain ranges in the Western US and of course the Andes and the Himalayas, so that's absolutely true. Some of what we are thinking about are watersheds, right? So water towers of the world absolutely is a theme of what we were thinking about, variability in those. And they also have major river systems, absolutely. But one of the main things from a climatic standpoint that we're thinking about is the Pacific Ocean, right? So these are 3 locations, seemingly disparate, but they are all connected by the Pacific Ocean and variability that happens within that system, right? So when we're thinking about maybe an El Nino event with warm tropical waters, right, we're going to impact atmospheric circulation that is going to also impact the Asian monsoon, North America and South America, right? Or La Nina-like conditions, the same kinds of things. So if we have coherent changes in the Pacific through time, which we believe we have, then we should be able to understand the different climatic variability in these regions and link that back with the Pacific. So one of the things that is most important with the Pacific, right, and one of the things that we'll be thinking mostly about here in the Midwest is what we call the Pacific North American mode. So this is a teleconnection that is almost directly, it's not directly, but very closely linked with the tropical Pacific and El Nino-like type of variability. So what I'm showing here are some different pressure systems. So this is like midway in the atmosphere. And the Pacific North American mode is really important because what I'm showing here in the upper left-hand corner is a correlation between an index. So it's just, it's either a positive or negative value. And it's just an index of numbers, and it is correlated with precipitation, right? So we can see here that in the eastern United States, we have a strong negative correlation with whatever sign, the sign of the PNA index. And in the Western US, we have the opposite types of signs. So what this essentially means is when we have a positive phase of the Pacific North American mode, It is characterized by strong low pressure over the North Pacific, strong high pressure over the eastern United States, and low pressure over the, western United States, and low pressure over the eastern United States. And what this does is it changes the shape of the jet stream, which influences atmospheric circulation. Right, so around these low pressure points, we have counterclockwise atmospheric circulation, and around these high pressure points, we have clockwise circulation. Now, what this does is it essentially, right, if we think about it this way, right, we're probably more accustomed to weather maps showing the position of the jet stream. When we have this positive PNA type of phase, right, we have a very wavy jet stream that brings this cold, dry, and sometimes snowy air down from the Arctic into the eastern United States. But at the same time, it's bringing up drier and mild atmospheric conditions into the western United States. And we often get more rainfall associated with this as well in the western United States, right? So this position of the jet stream is super important. During the negative phase of the PNA, we have basically the opposite types of conditions. So we still have our low pressure systems, right? But they have shifted. So now we have low pressure with counterclockwise circulation going over the western United States, and we have clockwise circulation over the eastern United States. And so this changes the shape again of the jet stream, which brings that cold air down to the west, and we bring that tropical air up into the eastern United States. So essentially opposite types of conditions, right? With these two different phases of the Pacific North American mode. During these negative PNA phases, right, when we have this warmer, moisture air being brought up from the tropics, right, we can often have what are called atmospheric rivers. Now, we've heard a lot about atmospheric rivers this winter, but mostly associated with the Western US, right? California got nailed with atmospheric rivers throughout this winter, 300% snowpack, right? They're devastating out there, and especially now that that's melting. But we experience these here in the Midwest as well. These are called the Maya Express, because as you can see, they come up from the Caribbean and the Gulf of Mexico across the Yucatan Peninsula into the Midwest. And so these can drive extreme precipitation. But in general, when we have these negative PNA kind of conditions, we're just bringing more moisture up into the eastern United States from the Gulf of Mexico. So that's just a little primer, because we will have to think a little bit about some atmospheric circulation as we think about climate flood relationships here in the Midwest. But the reason that this became a topic or a hot topic of investigation goes back to June 2008. So in June 2008, and actually they started in March, but they were probably the worst in June, there was a series of floods in the Midwest that brought this issue of climate flood relationships to a forefront. So again, this is from June 6, 2008. This was an atmospheric river that occurred over a few days, and it brought extreme precipitation to the Midwest in general. So this is a list of the states that were impacted by this atmospheric river. Here in Indiana, some of you may remember, this was a pretty major type of event. We had extreme precipitation across the central southern portion of the state in particular, with as much as 10.4 inches of rain in a 24-hour period. And we had, well, 6, 7, 8 inches across this region, right? This resulted in massive flooding. So this is a before image. We can barely see the rivers sort of outlined here with the Wabash River to the left and the White River along the bottom. And then during this flood event, right, this is what those rivers looked like. So this had a major impact on communities that were in the Wabash and the White River here in Indiana specifically, right? But there were other impacts elsewhere. These are just some of the most visible. So if we look at Martinsville, Indiana, here's 37 going through Martinsville, right? Columbus, Indiana, downtown, we have Haw Creek coming through Columbus, Indiana here. Massive flooding across, and it resulted in the FEMA designation of emergencies for counties across Indiana during this time. So some of the questions that arose from this were, how unusual is this? Is this a 1 in 100-year type event? Is this, is this something that is going to become more frequent because of increasing temperatures? What is the context for these types of events, and when have they happened in the past, is it consistent with this type of atmospheric circulation? What can we expect? Will we get more of these moving into the future? So one of the issues here is that we don't have a lot of paleoclimate records from Indiana. We have been working on that, and now we do. We've generated many. But when I started here at IUPUI in 2012, there were no paleoclimate records from Indiana directly. And so this question of what is Indiana's climate like? What can we expect from climate change in the future? How does it compare with the past, right? We didn't have answers to these questions because we just didn't have the data. And so when we got here, I started working on Martin Lake, which again is shown right here in the Oliver chain of lakes, located in northeastern Indiana in LaGrange County. It is a small lake, as I pointed out. Sorry if I pause every once in a while. I'm just checking the chat to make sure I'm not missing any comments or anything. It is a small lake, right, up in the northeastern Indiana in LaGrange counties, 12.9 square kilometer watershed, so not very big, especially when we're thinking about the White River or the Ohio River. But it is a relatively special lake, as we'll talk about. So it has what we call a stratified water column, and all that means is that the top of the lake stays generally pretty warm, and these are, stays generally pretty warm. It does freeze over in the winter. But the bottom of the lake is almost always very cold. And so one of the things that this does is it allows oxygen to exist in abundance in the upper part of the lake, but at the bottom of the lake, there's no oxygen. And this is great for us as limnologists, paleoclimatologists, because what it means is there are no little critters living in the bottom of the lake to mess up the sediments. And so every year, as we have productivity in the lake, algae bloom, sediment being washed in, whatever it may be, right? Those settle out in layers that accumulate over time and they're not disturbed. So essentially, each one of these light and dark layers can be thought of as 1 year of deposition. So this is very much like a tree ring in many ways. It has that kind of a resolution, or an ice core, where we're thinking about almost an annual scale of accumulation. The other thing that was really great about Martin Lake is it has these types of crystals. So these are calcium carbonate or calcite crystals, and they form directly from the lake water. So essentially these preserve the chemistry of the lake water at the time that they formed. And so they themselves are an archive of the chemistry of the lake and how it has changed through time. So we'll get back to that in a second.
And Broxton, there's a question in the chat asking if you think the depth, is the depth of the lake is what makes that difference in temperature, or is it something else?
Yes, so it is the depth in part. Sorry, I didn't clarify that. It's about a 17-meter deep lake. And so the temperature being, as we get lower, right, the temperature stays cold, and when it gets warmed up in the summer, it's really only heating that upper part of the water column. It doesn't penetrate all the way down to the bottom, so it stays cold. So we're thinking about basically a density difference due to temperature. So it's more dense on the bottom than it is on the top, and so it stays put, right? So it doesn't turn over. It's only in the winter for maybe a couple of weeks in like January or February when it's really cold and iced over, the water column has the same temperature throughout, and then it'll turn over briefly, and then it stratifies again. So that's how that works. Great question. I also often get asked, how do we generate these records, right? So we take, how do we collect our sediment cores? So this is just a little cartoon. We have our lake here on the left with the sediments from Martin Lake here. We use 2 inflatable rafts that are connected by a platform, and we have many different coring techniques depending on the types of lakes that we're coring. So this is just one type of example. But we have what's called a Livingston core that we then push down through the sediment, and we retrieve individual 1 meter length sediment cores consecutively until we get to the bottom. And by the bottom, I mean we get refusal. We just cannot push anymore. And usually that's glacial sediment for these types of lakes. It's too dense, glacial clays. And then we take an overlapping set of cores next to it so that the breaks in one set of cores, or between, in this case, drive 1 and 2, is captured in the middle of the offset set of cores that we collect. So in this way, we get all the sediment. There's no breaks, there's no gaps. Everything is nice and continuous. And when we bring that back to the lab, we can create a single composite record that is continuously spanning whatever length of time it is. And for the case of Martin Lake, we're thinking about 17,000 years. So Martin Lake is incredibly special, right? It is a hydrologically open lake. That means the water that is flowing in is easily flowing out. It's replaced within 3 months. And so this is important because this means that Martin Lake does not experience evaporation, right? It is basically the inputs equal the outputs. And so there's no modification from evaporation. And so this means that the chemistry of the water directly reflects the rain and the snow, or the chemistry of the rain and the snow that's feeding it, right? There's no modification of that afterwards. And what we have found with our work at Martin Lake is that there are basically, two-ish main sources, 2-3 main sources, right? So the Gulf of Mexico provides high oxygen isotopic composition precipitation from the Gulf of Mexico, right? So that's just, right, water is made of H2O. So the oxygen in that water, we can measure the chemistry of that, and it indicates that we have a high value of the oxygen from there, and that is coming from the Gulf of Mexico. Our other sources are either from the Northwest Pacific or the Arctic, but in both cases, they have very low values of this oxygen isotope that we can measure. And so we can use this to distinguish between persistent periods of getting moisture from one source or another through time. Right, so that calcite that forms in the lake, right, will preserve the isotopic composition of that lake water. So with that, right, we can think about changes in the source, and the sources are pretty seasonal as well, right? This is summer for the most part from the Gulf, and more winter cold season from the Pacific. The carbon isotopes that we get from the calcite as well can tell us about productivity or the length of the warm season, right? So biological organisms like the carbon-12, and so they take that up, that leaves behind carbon-13. So when it's warm and wet, it drives up that isotope. As these form, right, they provide a record over time. So lastly, we have the amount of sediment that is washed into the lake that also tells us about the occurrence of rainstorm events, and that is our percent lithic. So I do realize, I guess we started a little bit later, so I know that we are limited on time, so apologies, I will move along a little bit more quickly here. Sorry about that. But what we find with this, right, is that the isotopic composition of calcite at Martin Lake has varied substantially over time. And we have some general periods that we can think about. So we have this period highlighted in red, and this other period highlighted in red here, the current warm period, both of which have high oxygen isotope values. So what this tells us is that we are getting a lot of moisture from the Gulf of Mexico. And during this period in between that we call the Little Ice Age, which was a period of general cooling globally, we have low oxygen isotopes. And so this suggests that we are getting moisture from the North Pacific and the Arctic, preferentially during these times. So these are periods that are lasting for hundreds of years, as you'll see. We have our time scale here at the bottom. When we think about the calcite or the carbon isotopes, they look identical to the oxygen isotope. So what this tells us is that when we are getting moisture from the Gulf of Mexico, where temperatures are warm, and when we are getting moisture from the Pacific and the Arctic, it is generally cooler, right? So shorter growing seasons. And when we look at the lithics, we can see that we're getting more rainfall, right? During the medieval climate anomaly in the current warm period, when we're getting Gulf moisture, and we're getting more snowfall. So there's reductions in rainfall, switching to snowfall during the Little Ice Age, which is pretty consistent. So quickly, because I know we're running a little bit short on time, so I apologize for that. If we want to look at the relationship between flooding and climate, we are looking at these two lakes, one on the Ohio River and one on the White River, right? So the Ohio River, when we look at today, how frequently or when flood events occurred, right? We can see that they're mostly happening here in March. And so this reflects the spring snow melt, right? So we have snow over the watershed, and as that melts, it then runs off and creates a flood event. And this can basically be taken then as a measure for the amount of snow. When we're thinking about the White River, we can see there are many more events, January and then also into the spring. And these are associated with this type of atmospheric circulation, right? So coming up from the Gulf of Mexico, right? So these flood events reflect Gulf rainstorm events. So flooding on the White River reflects these rainstorms. Rainstorms don't cause flooding on the Ohio because they're simply just not big enough to cover the watershed. This is just an example of a rainstorm event. You can see they're long and they're linear. So while it could cover the entire White River watershed, they cannot cover the Ohio. So what we're looking at here for the Avery Lake on the Ohio, we're thinking about winter snowpack. When we're thinking about Half Moon Pond on the White River, we're thinking about rainstorms. So I'll just show these real quick. This line graph here is a accumulation rate. So when we have low accumulation rates, we have low flooding, high accumulation rates, high flooding. And so during this period, which includes the medieval period, right, we have generally low flooding. And then as we transition into the Little Ice Age, we have an increase in flooding. When we compare it with the White River, right, thinking about rainstorm events, we see basically the opposite types of conditions, right? So when the Ohio River was not flooding, the White River was flooding during the MCA. And during the Little Ice Age, the White River was flooding less and the Ohio River was flooding much more, right? So what this reflects when we think about it in terms of climate, the increase in flooding during the medieval period on the White River reflects an increase in rainstorms, whereas and a decrease in snowpack driving that decrease in the White River or in the Ohio River. And the increase in flooding on the White River or Ohio River during the Little Ice Age, right, reflects more snowpack during that time, which is pretty consistent. And this again reflects these anti-phase responses between small and large watersheds, rainstorm versus snowstorms. But importantly, both are flooding today, right? As we can see here, during our current warm period, the Ohio and the White River are flooding, right? And so our idea is that this reflects essentially a change in our watershed, right? So today, we're back in the 1600s, right? This is a reconstruction of virgin forest, right? We had widespread coverage of virgin forest. By 1920, we had a massive reduction with 90 to 95% of the Ohio River watershed deforested, right? So the idea here is that this coherent flooding during our most recent period, during the last couple hundred years, has largely been due to changes in land use that is increasing runoff on the watershed. I know that we have to sort of perhaps wrap up a little there. I do have some additional information and slides. So I don't know if folks want to stay on or not, or how we want to do that, but apologies for the excess information.
Well, it's a lot of information, and I'm sure people are thinking about the implications. And we do want to respect if people need to leave because they have a 1 o'clock appointment, that they can do that. But we always do hang around after we're done to continue conversations and to share some more information. So why don't we do a thank you to Broxton at this point for raising some very interesting questions and to make us think about things and to understand things. My takeaways is this is super complex, but super interesting. I'm very curious and I have a lot of questions for you. But let's thank everybody for also attending and invite you to attend future events. And so we'll officially end, but we'll let you just keep on going for a little bit for those that are able and wish to stay so that we could finish up your conversation. How about that?
Yes. So what I'm going to talk about next for those who are maybe want to is just how do we then use this paleoclimate information moving forward into thinking about our future with respect to rivers and flooding and things like that.
Okay, we'll carry on.
Awesome. Okay. So, right, we have seen these sorts of trends in the past, right? We have established sort of our climate flooding relationships. So turning to the modern, right, there are some studies that have shown that over the last few decades, right, we have had an increase in flood frequency across the Midwest. And if we look at Indiana specifically, right, we have a lot of blue triangles. So these blue triangles reflect increases in flooding frequency, red triangles are decreases. Indiana has experienced a tremendous amount of increase in flood frequency. The magnitude of floods across the Midwest is much less coherent. But again, for Indiana, we can see that here we are actually having both more frequent and higher magnitude floods. So this is something that is almost unique to Indiana. And these are attributed to our increases in precipitation. So on the left is a spatial distribution of increases in precip since the 1900s. And on the right is our bar graph showing these absolute changes for the Midwest region, right? And we can see that we have basically an increase from our baseline from like the 1900s to the 1960s, with an increasing trend in precipitation that is driving these current changes in flooding today. And the projections for both annual average and for heavy precipitation are increases, right? So continuing the trends of increases in precipitation, both annual average and heavy precipitation into the 2070s and likely beyond. So flooding is obviously one of the implications, right, for this, right? But what are some of the other implications that these types of changes in flood frequency and magnitude might have on our landscape? Does anybody have any thoughts?
Well, where does all that water go? That's what I wonder. So does it change the course of rivers, or when it
Yeah,
spills
that's
over?
absolutely, that is a great question. And you're actually correct, right? So yeah, so we have changes in the flooding, right? But flooding is not the only thing that happens when rivers are flooding, right? We also have changes in mobility, and that is in erosion. And so those are some of the biggest impacts that we can have from changes in rivers. So this is just an example of one river from the White River here down by Petersburg on the southern White River, showing that we basically, we have increases in discharge, right? So we see this, that is true. So it's not just flooding events, right? These are also just discharge in general is increasing. And these increases are, again, not just due to increases in precip, which they are, but specifically increases in precipitation from the Gulf of Mexico. So we have more frequent, more consistent warm season like atmospheric circulation driving that Gulf moisture into the mid-continent. And so when we look at rivers across Indiana, right, we have to think about the impacts of the increases in discharge on the river systems, and specifically with respect to mobility, right? So flooding is one thing that happens, but when the rivers are full of water, they are also eroding their channels, both on the bottoms, but also on the sides. And so if we look at this map here shows the distribution of mobile streams across Indiana. So the orange ones are the mobile streams, most mobile, and the blue streams are those that are most stable. And so we can also look at this from a graph standpoint here. So these on the right are all mobile streams, and the one with stars are the ones that are mobile streams within the White River watershed specifically. I'm just reading a question here. I'm curious about whether that would moderate silt deposition similar to pre-Aswan Nile River, and if that would change fertility of soils in these river basins. Yeah, I mean, so one of the things that we have seen from the lake that we've done, or the work that we've done on these floodplain lakes, is that there is a tremendous amount of silt that has been eroded and deposited in these floodplains. So on the Ohio River, we have a 10-meter long core that's 3,000 years, but the upper half, the upper 4.5 meters of that is only 200 years old, right? So that is, you know, we go from 500 years per meter to 50 years per meter in terms of time per core. So it is a tremendously huge amount of sediment. So it could potentially increase fertility, right? But we're also losing that soil from our agricultural fields and other things. So it's a repositioning of that sediment in the system. So some areas will benefit, others will not, right? And these changes in stream mobility as we're eroding sediment with increases in discharge, right, will impact not just the communities that are being inundated, right, but they have tremendous impacts on infrastructure, right? So this is near Centerton, Indiana here. This is a bend on the White River that is moving towards these utility lines right here. And then this was March 2005, and in April 2012, it had moved, and they had actually moved the utility lines as well. This is subsequently cut off, so it is no longer a threat here, right? But there are many other locations, this on the White Lick River here, showing mobility changes from 1998 here on the left, where the bend in the river was 865 feet from the highway, whereas here in 2012, it was only 620 feet away. Now, if you did the average, you might be like, oh, we still got 35 years until this is going to intersect the road. But something that's important to recall here is that these do not happen. It's not just every foot a year or something like that, right? These are things that will erode tremendously in a single event, right? So you could move 200 or 300 feet in a single event. So this is very close proximity and threatening these types of this type of infrastructure. And what we see from our data, right? So this is the Half Moon Pond clastic flux showing increases in flooding with higher values, right? Is that these values in the most recent part in the current warm period are more sustained and higher than at any point, at least in the last 1,500 years. So with this Half Moon Pond data, with some of the flood reconstructions that we've been doing here in Indiana, we can show that these current trends are anomalous within at least the context of the last 15 or so 100 years. So one of the things that we have been doing is working with the Fluvial Erosion Hazards Program that is sponsored in part by DNR, and is also in conjunction with the Center for Earth and Environmental Sciences here at IUPUI. And they have been mapping fluvial hazards across Indiana. And so here we have an image of Indiana with all of the different fluvial systems, right? And the idea is that we have many streams that are highly mobile and causing fluvial erosion hazards at different locations, right? So Sugar Creek near Crawfordsville, right? We have houses, homes that are being impacted by bank erosion, right? The Whitewater near Brookville over here in Eastern Indiana, right? We have infrastructure being impacted by fluvial erosion. And so what the FEH program has done is in part working to map not just the rivers, right, but the different areas that are at risk from these fluvial hazards, right? So this is this first image up here on the right is from down here where this red box is on the lower White River near Petersburg, Indiana. So this is, Petersburg right here. And this is Half Moon Pond, our study area. So here, this light white shaded area reflects the floodway, right? So this is the inundation area where when we have a high flow event, this is the area that we can expect to be inundated, right? So this is valuable for people that are looking to build, if you're thinking about building roads, building homes, communities, whatever it may be, right? We can look at these different types of maps and understand, are you at risk for flooding, for fluvial hazards? What this also does too, and then in purple, what we're looking at here is the fluvial erosion hazard area. So these are areas where the discharge is the highest, the flows are the highest velocity. And so we could expect erosion to occur in this corridor, right? So if you have a building or something in this area, right, you could expect it to be impacted by undercutting or being eroded by high flows. One of the things that's important about this as well is that the Half Moon Pond data, right, we can look at how flooding has changed through time, but simply by looking at how old the lake is, meaning it's about 1,500 years old, this provides us information about how the lake moves across its floodplain over time. There have been suggestions that basically rivers in Indiana are stable and they have been in their current plan form. That's just the way that they look when we look at them on a map since the last glacial period, and that they haven't really changed much and that their positions and their shapes basically reflect high flows from glacial times. But what we can say using data like Half Moon Pond is that, well, no, actually, the White River was in the northern part of its floodplain here about 1,500 years ago. You can't see it exactly, but there's another lake right here called Long Lake that is another channel from the White River that's younger than Half Moon. And then we have the actual current White River channel here. So what we can say with this data is that these are highly mobile streams through time. They're maybe even more mobile today, but this is a highly dynamic area that needs to be treated with respect and giving the river room to move as it responds to climate change. So besides just, I'll just back up for a second, besides just climate, right? What is one of the things that might be driving some of the flooding and erosion hazards that we're experiencing today on our rivers here in Indiana? Right, so yes, climate is a factor. Yes, we are getting more rain, right? But there's another factor here that's really important, right? So yes, global warming, right? We have our climate change, right? So we're adding more water to these systems, absolutely. But we have also changed them, right? These are existing in a fundamentally altered landscape, right? It's been deforested, right? But it has also been modified, right? Additionally, beyond just taking out the forests, right? We have also constrained our rivers, right? So this is an image of the White River levee near the Meridian Street Bridge, near where I live in Warfleet. And when we build these levees, right, we are fundamentally restricting the area that can be flooded, right, and the area in which these rivers can move. And so when we do this, when we disconnect rivers from their floodplains, right, we can greatly increase discharge, right? So if we have a community, right, up here, we have a nice house, we want to protect our houses that are in floodplains. And so under one type of climate, we build our levees, right? Just like we have done on the White River and many other rivers. But as we change climate, right, or if we change other land use practices, right, and we increase the amount of water flowing through these rivers, right, we have now increased discharge and the power, stream power, along with that, and we get incision. And eventually with that incision, right, we have also increased lateral mobility that will undercut our levees and homes and other things until we get to a period of stabilization and a new equilibrium with the type of discharge and stream parameters that we have, right? And so floodplain connectivity is really one of these other factors that is super important when considering the causes of flooding and the impacts of this. So this example here in the lower right is actually a relatively well connected floodplain on the upper White River in Delaware County. So this cross section here, right, it just shows basically going across the floodplain, right? So this steep bank is this bank on the lower part of the picture, and then the floodplain over here is on the upper side of the picture. When the river is full, right, we call that bank full. When it is basically up to and should be about to spill out onto the floodplain, we can see that it is not spilling out on the floodplain. So this is what we would call a moderately entrenched stream. It's only once we go double basically to our flood stage that it starts to spill out across the floodplain. And then when we get to our 100-year floodplain, then it is clearly spilling out. So this is actually a relatively well-connected stream, and this can help moderate some of these types of flows. Something like this that we have down at the White River in Indianapolis and whatnot, right? We have levees that go through the city, right? They stop at the southern part of the city, and then that water can spill out onto the floodplain below that, but not before. So one of the ways that we can start to address some of the flooding issues might be to reconnect, right, some of our rivers to their floodplains. This can help reduce flooding. So one aspect here, right, we have two different hydrographs, right? One will show, or one shows basically when we disconnect these types of floodplains, we increase the peak discharge, right, during a flood event, because we've restricted the area that can actually flood, so it increases the height of that river. Whereas when we connect it with the floodplain, right, we decrease the height of the peak and we experience a longer peak, right, but it's more moderated, it's more spread out. It's a lot like in the early days of COVID, right? When we were trying to flatten the peak so not everybody would get COVID at once and flood the hospitals, right? Because that's a problem. If we get sick sort of more spread out and we can get treatment and go in, and that's a much better situation, right? It's a very similar thing with flooding, where if we have all the water coming through at once, then that's going to create problems. If we can spread that out over time and reduce the peak flow, then we reduce the amount of problems that we have, right? So a narrow spillway, high discharge, lots of problems, right? An expanded floodway, we can reduce our problems and accommodate that flow. All right, so how do we restore these floodplains though, right? In the EU, because this is a global problem, right? We are having increased discharge here in the US and in the Midwest, right? But the EU has been also dealing with this, and they have come up with this Room for the River program. Essentially generating blue-green types of riverways. And they have done a lot of different things, right? One thing is moving our dikes or levees further back from the river so that we can give the river more room to flood. They've actually removed sediment from floodplains to create additional accommodation space, right, for floodwaters. Other things are like removing obstacles. You'll notice in this image up here on the right, this bridge here has an ability for the water to flow underneath it. Same with this bridge up here. This is intentional so that we don't add obstructions into the floodway, and so we can allow the floodwaters to move through. We can also add things like green rivers or side channels to accommodate overflow. So we can still have levees, but then if it breaches that, we have alternative routes for that water to move through. Right, but then the question should be, and this goes back to some of the work that we're doing, is how should floodplains actually be restored? Sorry about that. One of the things that we can do, right, is we can go again to the paleo record to look at what were rivers like before, what were the environments around rivers like, and does that make sense to try to restore them to those types of conditions, right? So in these floodplain lakes, like Avery Lake, Half Moon, whatever, right, we can look at the flora. An example from Avery Lake that goes back 3,200 years here actually shows 3 periods of human occupation. So the Balmer and the Mississippian were periods of occupation by pre-Columbian Native American populations at that site. And we can see the decrease in tree pollen here. So this is hickory that I'm showing here. So we have decreases here, and then during the Mississippian, and again today during our occupation, right? But we also have recovery. And so we can use pollen data to understand once a system is disturbed, how did it grow back? And we can maybe try to emulate some of that regrowth to understand how we should reconstruct some of these floodplains. We can also understand the biology, the fauna that was present there through sediment DNA to actually understand the types of fish species and different diversity of species that existed in different environments in the past. And of course, we can also look at changes in water quality, both modern and present, with a variety of different types of techniques. And the last thing that I was going to talk about was just some of this floodplain restoration. And I was going to ask you all, right? So we can restore these, right? There's clear benefits from a flood perspective for restoring these, right? But what are some other additional benefits that we can get from restoring floodplains, right? So yes, they will reduce floods, but what can we do to, or what are some additional benefits, right, that come from this? I'll give you one thing, right? We were working with the Nature Conservancy. They're very concerned about increasing habitat and resilience in our ecosystems. So here's our example from Denmark, right? The river was channelized in this red area here and subsequently was restored to a more natural channel, right? And you can see the increase in green space, right? So we're increasing habitat, right? Yeah, reducing financial loss, absolutely. That is a huge one, right? If we reduce floods, we're not going to have as much damage to infrastructure and whatnot. From an ecological standpoint, though, by increasing habitat, we're also increasing our biodiversity and resilience. Another big one, actually, is we can help fight climate change in this way, right? We can actually increase carbon storage in floodplains by increasing habitat, wetlands, and carbon sequestration in these types of areas. And of course, improve water quality. And that is very important, right? We have all sorts of things flowing through our rivers, from microplastics to PFAS to whatever, right? There's flame retardants, all sorts of different stuff. Too much phosphorus, nitrogen, other types of agricultural chemicals, things like that. So we've been working, CEAS has, to reconstruct, that's the Center for Earth Environmental Sciences here at Indianapolis, IUPUI. To restore areas like this. So this is Fishback Creek. This is Eagle Creek right over here on the right. This was all farmland right here in the, well, up until about the 90s. And subsequently with CEAS, we have worked to restore much of this area, right? So this field you can see is still in use, but much of this area has been restored and is wetlands. It's beautiful. You should go walk through there. There's a nice parking area up here and a boardwalk through the wetlands. It's quite nice. Right, but this helps to increase our habitat, our biodiversity, carbon sequestration, and water quality for here in Indianapolis. CEAS has also been working right here in downtown Indianapolis, right? So this is the White River. Here's Indianapolis. I'm over in this building, just over here. And prior, in the 90s, prior to about the 2000s, right, the White River was devoid of riparian vegetation or trees growing next to the river, right? As we can see here today, right, CEAS has worked with Lilly and other groups to plant trees and to revitalize these greenways along the White River down here in Indianapolis. There have also been some other areas where we're working to, sort of modify agricultural practices in order to reduce runoff of agricultural nutrients, things like that, because right, these things ultimately end up in the Gulf of Mexico. So trying to restore those types of things as well. And down on the lower White River at Half Moon Pond, where we did our study, this is also an area of interest for the Nature Conservancy to try to increase habitat and restore much of the floodplain in this area as well. So there's lots of benefits beyond just reducing flood damages and whatnot, but lots of financial as well as other types of benefits. So we can collectively call these things green infrastructure, right? These are, there's a lot of intersectionality here. They help with flooding, but also with lots of other issues related to climate and whatnot. So yeah, with that, I will thank you for sticking around and having additional conversation. I'll hang out and we can talk about any of the myriad of topics that we cover here. But this really, this is my last slide, because really this is a tremendous group effort, many students, lots of funding agencies, and over a decade of work going into a lot of these findings. So I have to thank all of the students that have worked with us, but thank you as well for listening.
Well, you're getting lots of claps and stuff.
Awesome.
Yeah, for all this information.
Yeah, I know it's a lot.
It's a lot. It is a lot. So that my takeaway is that this is super complex, and I wonder about how we translate this to the general public that likes to have things in like one word about the importance of this, because what you're talking about is it's going to take time. It's going to take working together to be responsible about this. But oh my gosh, how do I tell my neighbor? Like,
Yeah. No, and that's a great question. And it's actually something that we are working on. So one of CEAS's missions, we have really 3 pillars: research, education and outreach, and stewardship. And so we do all of those things, and we are working constantly to break this down into, this is a 30,000 foot overview of many of the different things. And so when we do try to translate these, we do often focus these into more specific areas, projects, whatever that might be, but they are all part of this larger integrated project to increase our resilience. If we had to come up with a word, I would say resilience is the word.
Well, it seems to me the good news is I can understand everything you're talking about. It makes sense. It's engaging.
Excellent.
But at the same time, it's
Yeah,
just like
yeah,
I also might feel like, oh my gosh, where do we start? Where do we begin?
yeah.
Right. And what do you do first? And so then I might just like, well, Broxton will figure it out.
Yeah. I think there are a lot of groups. So we're starting to work a little bit with KIB. So Keep Indianapolis Beautiful. I think some of these types of organizations are excellent ways to get started. Our students here at IUPUI are helping with here along the White River, places like that, through our stewardship initiative. So we are engaging people to come out to participate in species, invasive species removal, to work on different aspects of this. And so I think the best way is to reach out and to get involved with local organizations like KIB, like CEAS, if you're a student here at IUPUI, to actually get in here and start doing some of these actual activities to address some of these issues.
We have a hand raised. Go ahead.
Yep.
Great talk, Dr. Bird. Question for you. A lot of this floodplain, I gotta imagine, is agricultural land.
Yeah.
How are the farmers, the local ag people, how do they deal with this kind of idea that maybe we need to take away some of that?
Yeah, and I think that's a great question, because with the agricultural fields, it's actually, they're probably less impacted than, say, communities, like cities that are maybe being flooded, that's a different thing, that maybe do we need to relocate or something like that. But a lot of times farms are, farmed normally, and then they're also designated as flood storage. So if things flood, they may flood that area or something, and they might need to be compensated if they lose agricultural yields because of that. But a lot of times we actually have a lot of buy-in from the farmers in the area. We've actually been working with farmers to help reduce, collaboratively to help reduce runoff, but also nutrient runoff and things like that. So we are having a lot of coordination and collaboration with the agricultural community. So this is definitely not something that we are trying to go in and impose or tell people what to do. We are really working with the agricultural community to solve these issues together. And they recognize the issues because they're losing soil, they're being impacted by floods, they're losing land. What's taking away land is the erosion that is occurring as these streams are becoming increasingly mobile. And so working to decrease that mobility is actually in their benefit as well. So we actually have very good collaboration with them. So that's great. That is an important question.
Yeah, California could learn something from that. With Tulare Lake reforming, one of the best things we could do is just let it stay there and have it be a natural flood basin. But there's billions of dollars worth of loss that will last for years now because of this. So, well, that's good news to hear that they're so receptive, and great job again.
Yeah, thank you. So far, so good.
Jose,
I see another one from Jose.
Hi, Broxton.
Hey.
Nice seeing you, and great talk. Thanks for all the information they're giving us. And my question goes, it's a more localized question, going back to Indiana. The issue is, I want to ask you if you or any of your collaborator, funding agencies or the Nature Conservancy, any of your collaborators have had any, or were called to do any or perform any input on the discussion on the legislature about the bill to change the language, talking about flooding zones in Indiana, specifically the bill that will reform the fact that you will have to use the best available maps. They wanted to change that. Were you cited or summoned to explain all of this research, or any of your collaborators that you know?
Yeah, so Bob Barr is one of my main collaborators at CEAS, excuse me, at CEAS here. And yes, we have frequently given testimony at the Indiana State House just down the street from us here in downtown Indianapolis. So yes, we are constantly providing feedback and speaking on behalf of agencies that may not be able to speak as much because they are government run or could be influenced by political situations. So we provide, as academics, we provide our academic cloak of neutrality because we are just data driven, right? We are not here to advocate for one position or another. We are just here to convey the data and what the consequences may be of one decision or another based on data. So yes, we have provided insight into that. And our hope is that that will be listened to and that legislation will not necessarily go through as it currently stands, because it does not necessarily make sense to not use the best available data, obviously. But I think that, you know, engineers know that, and just from a fiduciary responsibility of their own to create the best products and whatnot, they will still likely use the best available data, because otherwise they may be liable if they don't. So, well, I'm not sure how much impact the legislation would actually have, but we are, you know, providing our input as to what some of the impacts could be for that. Absolutely.
Great. Thank you. Thank you.
Yeah, thank you. Yeah.
Broxton, I was wondering about when you said reaching out to organizations. I'm aware that many counties in Indiana have a community foundation that tries to address, you know, the needs within the county. I wonder if that would be another place to connect with, because you know, those folks might care about stuff like this. And I think about my own town has a corporation development council, and I know we talk a lot about if there's going to be development, is this on a floodplain, near flood? What's the impact of that? So there are some people that do talk about it. That might be another place to share.
Absolutely.
Data.
Yeah, no, absolutely. And so again, Bob Barr is our spokesman for, mostly for the fluvial erosion hazards program that is sponsored by DNR, and we reach out to communities, community agencies, nonprofit. We do extensive amounts of outreach with that, and so we're always looking to increase that as well. Bob gives maybe 50 talks a year about fluvial erosion hazards, about the different tools that are being made available to communities, to government agencies, whatever, in order to help decision-making processes. So that is an active part. And yeah, this talk could have been 2 more hours with all the different stuff. So, you know, I take that to heart, what you say, and we are trying to do our best. And if you have any interest in hearing of any of this, or your community organization does, you know, we can talk more if anybody here that's listening to it does. I mean, we are happy and willing, and it's part of our mission to go out and to talk to communities and to convey not just the hazards associated with fluvial systems, but also the tools that we are developing to help communities make decisions. Part of our process is also developing a post-flood recovery plan. So once a community or an area may experience extreme flooding and damage from a fluvial event, how do we move forward, right? Do we just go back to what we were doing before? Or how can we build in a better, more responsible way moving forward? So that is also part of what we are doing with the fluvial erosion hazards program here at CEAS.
Well, thank you again. Many thanks to those who were able to stay on. Obviously, this is an important conversation, and you've given us lots to think about. So thank you for being our Scholar of the Month, Broxton, and the work that you do. Appreciate it.
Thank you, and apologies for it being a little longer than anticipated, but all good. All right. Well, thank you all.
It just means that there's lots more discussion to be had, I think. So
yes, absolutely.
Yeah. Great. Thank you all for coming.
Okay. Thanks a lot.